All right, I guess it's about time to start. Let's see if our friend Professor J wants to join. Probably. We'll see. Okay. All right. So I was thinking that today we would do maybe one or two more examples of Bayes' theorem because we should have done them the other day, and then we'll move on to a little bit of graph theory, maybe, just for, S's and G's. Yeah, Monty Hall problem 2. Yeah, that's... Yeah, so welcome to the... We could do a whole class. It's like, welcome to the introduction to the quantum Monty Hall problem. So, okay. So let's do a little bit of combinatorics and probability first. So we select from a deck. We're going to select the 4 kings and 3 of the aces. So just, I guess, not the ace of clubs. For whatever reason. Wow. Quanti Hall problem. That's it's pretty impressive. So, okay, so we select 3 at random from the 7. So what is the probability? This is like a good all-around question because it requires a bunch of... oh yeah, I have my window open, so that bird is just going nuts. So, okay, what's the probability that at least one ace is chosen out of the 3 that we pick at random, right? Actually, this problem, part 2, is easier, but let's just do part 1 first. Okay. So what is the probability that one ace is chosen? So if we're going to choose one ace, then we have 2 buckets, right? We have the aces, where there's 3 of them, and we have the kings, where there's 4 of them. And so the number, basically, we want to know the at least 1. So what if we want to know the probability that exactly 1 ace is chosen? So let's just say the probability that ace is equal to 1. So eventually we're going to have to do the probability that ace is bigger than or equal to 1. But let's just calculate this probability first. So this probability is equal to, as it turns out, well, you can choose, out of the 3 aces, you can choose 1, times, out of the 4 kings, now here's the question. How many left do we have to choose? What goes into this slot here? And this is a multiplication. And then what do we divide by? So the total is equal to the number of selections out of 7 objects. We pick 3. So that's a 7 choose 3 down here. Yeah, that bird is doing its job. So here's the thing. Now I'm inside, but I have my window open. Okay. So, as it turns out, when you add up these 2 numbers that we pick, we have to get 3. So this number needs to be 2. So this is basically the number of ways that this can happen, the probability that ace is equal to 1. So if we ask, like, what is the probability that, let's say, ace is equal to 2, we would get something similar. It would be, well, 3 aces, we pick 2 of them. 4 kings, we pick 1 of them. And then we divide by 7 choose 3, which is, again, I guess there shouldn't be a bar over 3. 7 choose 3, not 7 divided by 3. Okay. And then, of course, the last thing that we can compute, the probability that there are 3 aces, is 3 choose 3. Now that's just 1 times 4 choose 0. That's just 1 again, divided by 7 choose 3, whatever that is. Good, I can convert that. All right. So these are all the probabilities that we get. That we get 1, 2, or 3 aces. So the probability that at least 1 ace is chosen is this number plus this number plus this number. So this whole thing is equal to the probability that we pick at least 1 ace. There's an easier way to do this on the other hand, right? If we know that we're going to pick at least 1, then that just means not 0. So as it turns out, this is all the same as if you were brave enough, you could do 1 minus 3 choose 0, 4 choose 3, divided by 7 choose 3. And that would be an equivalent answer. As it turns out, that's equal to all of these things added together. Now, 3 choose 0 is 1, 4 choose 3 is 4, so this is 1 minus 4 divided by 7 choose 3. 7 choose 3 is 7 times 6 times 5. We are divided by 7 choose 3 because from the 7 cards, we pick 3 at random. So the total number of ways to pick 3 things out of 7 things is 7 choose 3. And so that's why it's the denominator of everything. All right, cool. So what is 7 choose 3? It's equal to 7 times 6 times 5 divided by 3 times 2 times 1, which is equal to 7 times 5, which is 35. So 4 divided by 35. So this is equal to 31 divided by 35 is the probability that we pick at least 1 ace. Let me calculate this with a calculator machine. Yeah, it's kind of like it's like a percentage. Basically, we calculate, here is the total number that satisfies whatever we're doing. Wow, that's really bad. Let's just write it in text. We could just say, this is the total number that satisfies the condition. I think I might be able to move this. Yes. Oh, sorry guys, I hit the microphone. Hopefully that didn't blow out any of your eardrums or something. Okay. Yeah, I can type. All right. So that was all just number 1. Beautiful, beautiful. What is the probability that the ace of spades is chosen? Well, that is one specific card. So the probability that a specific card is chosen is... How do we want to compute this the best way? So this is the place where we did all this stuff. So we want just the ace of spades. So this is part 2. So if we do part 2 and we want just the ace of spades, then what that means is that what we're going to do is select. Yeah, so if we know we're going to pick the ace of spades, there's literally one way to do that. And then the question is, how many ways are there to do everything else, right? And as it turns out, there are, and I guess it really doesn't matter, there are 6 cards left and we have to pick 2. This is easier than I was confusing myself for a second, but yes, this is just 6 choose 2 divided by 7 choose 3. The reason why is because we remove, actually, you guys are right. I'll just type it. So you remove a single card from the total, and then you also remove one card that you have to pick. So let's see, 7 choose 3 was 35. 6 choose 2, on the other hand, is, what is that? 6 choose 2 is 6 times 5 divided by 2, so it's 15. I guess we can factor out the 3's, or I'm sorry, the 5, and we can say that this is 3 over 7. 3 over 7 is something. Probably what, like 0.14 times 3, which is 0.42 something. Yeah. That's correct, a decimal number, 0.428. All right. So now let's go and steal a new part of the question, because we still need to do that. So now this part we can answer right here. There's enough space. Yeah, less than 1. I'm glad that his opinions have filtered into this class. So, what is the probability that all 3 aces are chosen? Well, if we're going to pick all 3 aces, then that is 3 choose 3. And then we're going to do 4 choose 0, because we're not going to pick anything else, divided by 7 choose 3. So, as it turns out, the probability that all 3 aces are chosen, since 3 choose 3 is 1, and 4 choose 0 is 1, this is 1 divided by 35. Which should be about, what, 2.9%? Is that right? Oh, I'm wrong. It's 2.8%. Okay. All right. I have no idea. That's not even my dog. That's just neighborhood dog bark. Okay. So here comes some conditional stuff. So now we get to use some conditional stuff. So if it is known okay, if you want to know the big picture to get out of Bayes' theorem, the big picture is that if you need to know the probability of A given B, and all you have is the probability of, say, B given A, Bayes' theorem allows you to swap these two symbols and write it as the probability of A given B is equal to the probability of B given A times the probability of A divided by stuff. And now that stuff is basically comes out of a partition, right? Where you take the whole sample space and you break it down, let's say, into A1. Let's just call this A1. And then this will be A2, and this is A3. The point in dividing by 7 choose 3 is that it's the total number of options. So remember that if you do something like 6 choose 2, this is just a number, right? This is just, what is this? 6 times 5 over 2, so this is just equal to 15. So that's not a probability, right? Whereas 6 choose 2 divided by 7 choose 3 is a probability, right? Is a probability because Yeah. Because you're dividing by the total number of options. Okay, let's go back to... let me just use the mouse because it's hard to scroll with a pen. Okay, so what we're going to do here is if it is known that one ace was chosen, what's the probability that all three aces were chosen? So, okay. Cool. So if at least one ace was chosen, so we have at least one ace. I guess I can actually just type this. Maybe it'll be faster than writing it. If at least one ace was chosen, what is the probability that all three aces were chosen? Ooh, Lord. Okay. Now let's erase this crap. All right, so let's deal with this probability. So if at least one ace was chosen, what's the probability that all three aces were chosen? So this is the given thing, right? So this is, we're asking for the probability that all three aces, given that at least one ace. So you can actually calculate this because we know that this is equal to the probability of all three aces intersection at least one divided by the probability of at least one ace. Now, notice that we've actually computed both of these things. So the probability of all three aces, well, actually, what we should say is that the intersection between all three aces and at least one ace is what? So if I tell you that you've selected all three aces, but you've selected at least one ace, right, then you know that you've selected all three, right? I guess I can just type that out. If you have selected at least one ace, but also all three aces, then you've selected all three aces. Oops. And you don't need to worry about the at least one part. And so what this is going to do for you is it's going to allow you to say, this is really just equal to the probability. I know, it's definitely weird, but whatever. So it's the probability of all three divided by the probability of at least one. And so we've computed all these things. The probability of all three aces is 1 out of 35. And the probability of at least one ace was 31 out of 35, if you remember the answer from the previous slide. The 3D effect, I think, is some kind of weird bug, so I hope it doesn't stay, otherwise it kind of makes it a little bit, I mean, it's cool, but it makes it definitely unreadable. So here we get 1 over 31. All right. Okay. Let's do one last question. If it is known that the ace of spades was chosen, what is the probability that all three aces were chosen? Okay, so how is this different than the other problem, right? So, well, okay, I guess it's pretty easy to see, actually, because if it is known that the ace of spades is chosen, it's just a different number, right? So that's part 2 here. Yeah, sure. So the thing is that if I say you've done two actions, those two actions are you selected all three of the aces and you've selected at least one ace, but there's only 3 aces to pick, right? So if I say, you've walked into a room and you've picked up at least one candy bar, but then you picked up 3 candy bars, saying that you picked at least one was duplicative. Like, it doesn't add anything. So because it doesn't add anything, it's just irrelevant, right? So you can kind of say, like, here's the all 3, and here is at least 1, right? All 3 is part of at least 1, but since it's a complete subset like this, when you intersect them, you just get the center part. Okay, so let's talk about the difference. So then the probability that you select what? Given that you've selected the ace of spades, and then this is the probability of all 3 aces. Now, this is really the same thing, right? Because so the probability of all 3 intersect ace of spades. Exactly, it's just redundant. Divided by the probability of ace of spades. So we just have to recall our answers from the previous thing. So this is 1 out of 35. This part here. Divided by the probability of the ace of spades, which, if you recall, was that 6 choose 2 divided by 7 choose 3 thing. I'm sorry, I put a division sign in there for no reason. Maybe I can pull it out. Almost. So, yeah, so this is 1 out of 35 divided by 15 out of 35. And then you can just remember the rule A over B over C over D is equal to AD divided by BC. And so here, these are going to cancel, and so you're just going to end up with 1 over 15. So 1 over 15, let's look at the previous problem. So this is 1 out of 31, and this is 1 out of 15. So actually, if you know that you've already selected the ace of spades, you are, I guess, more likely to have picked all 3 aces. Huh. So I'm trying to think of the answer to that. So here, you've picked at least 1 ace. And here you've picked the ace of spades. Well, let's think about it here. Or is this the right number? I think it is. Okay. It's a bit counterintuitive. Yeah, so either I made some kind of mistake here, or it's just counterintuitive. I'm not sure which it is. I mean, I'll tell you that the calculations we did for all the parts are correct. So that's at least good. Yeah, let me try to think about this for just a second. Why this thing is less likely than this? I guess because no, I'm not 100% sure. I'm not sure I have a good explanation for why this is like this. So the probability of at least one ace is this. And the probability of having picked the ace of spades is this. Okay. Yeah, so... Oh. No, okay, never mind. Okay, so... let's move on to a different problem. I'm going to try to think of a good explanation for this. Either that or it's not true, but I think it is definitely true. Well, so there's a lot more possibilities. You know, I think the way to think about it is that there's just a huge number more possibilities if you pick, for instance, here you're restricted to the ace of spades only, and you know you basically take that one out of circulation, so you really only need two more aces. Here, on the other hand, you have a lot more options. Like, you know that the probability of at least one ace means you could have, what, the ace of spades or the ace of hearts or the ace of diamonds or whatever, and so when you add up all those different possibilities, plus getting 2, plus getting 3, that's just more options total. Doesn't sound very convincing, but I think that's the best explanation I can offer right now. Yeah, so in both cases, there's 2 aces left out of 6 cards. Well, no, I shouldn't say that. So there's not actually 2 aces left out of 6 cards. In this case, where we choose at least one ace, it could be that we actually pick 2 aces. Or we could pick all 3 aces, right? So in the case where we pick just the ace of spades, I guess we know a specific card that we pick. Yeah, I don't think I'm coming up with anything that's like absolutely perfectly compelling here. But the calculations are actually right. So at least that's good. Okay, let's see. Should we do an urn problem? Let's see. Oh, I think this one was... The reason why I included this urn problem was that it was somewhat interesting. It was different. So urn N contains 5 reds and 10 blue. Urn D contains 2 red and 6 white. Oh, I guess change this to blue. Or change one of them to... Yeah, just change this one to white, I guess. Wow. Okay, if the nickel falls heads, a ball is chosen at random from urn N. If the nickel falls dimes, from urn D. And then here's the weird part. If both coins fall on heads, 2 balls are drawn. So what is the probability that at least one is drawn, right? So this is a different one. You cannot actually just draw a tree out, because the thing is that, you know, you would say either in most cases you'll just draw that you'll pick from the N urn or the basically N bucket or the D bucket, right? And then you'll either choose red or white, red or white. So that's pretty simple. The problem here is that if the coin falls on both, then you pick out of both of them. So the thing about these trees, one thing that the tree requires is that the sum over all the different branches, so if you have, like, say, 3 different branches, it requires that the sum of all the probabilities here is equal to 1. And it requires that you cannot go down multiple branches at the same time. So here, if you just drew these 2 things, then you would say it's actually not so good, because what you'll get is something where you can go down both the nickel branch and the dime branch at the same time. So that's not what you want. So what we're going to do instead, and I'm going to try this out, I think that this one it's different than, things in the past. So in order to prevent going from multiple branches, I'm just going to call this just nickel. This will be just dime, right? This will be, I guess, if a nickel falls heads, the ball is chosen from. I guess technically the problem also doesn't say if they both fall tails. There's also a neither option, right? And this will be the both option. So if it's just nickels that comes up heads, then it contains 5 red, so red and white, red and white. So here it contains 5 out of 15. And so the probability here is just 5 out of 15. I guess we don't have to care about the white probability there. And then Urn D contains 2 red and 6 white, so it's 2 out of 8. 2 out of 8. And again, we don't really, this is 6 out of 8, but we don't actually need this for anything. So, and then when we have both, we're going to have to pick out of both urns. So what is the probability of getting a red ball if we pick out of both urns? So actually this is like a it's a inclusion-exclusion principle thing, where you'd say it's the probability of picking out of the nickel urn, a red one, plus probability of picking out of the dime red, minus the probability of picking out of both. Right? Because if you pick a red from both of them, right, you just want at least one red ball. So the probability here is 5 out of 15. The probability here is, what is it? 2 out of 8. But then you have to subtract off the probability of picking both. What's the probability of picking both? As it turns out, picking out of these urns is independent, right? So what we're going to say is that it's actually equal to minus 5 over 15, which is, I guess, just 1/3 times 2/8, which is 1/4. So here we're going to get 1/3 plus 1/4 minus 1/12, which is equal to the probability of picking at least one red here. And then this is red equals 0. I guess that's the same thing as picking white, right? Because red is equal to 0 here. And same thing here. Red is equal to 0. And then if you pick neither, then that's also a problem. So, okay, so what is 1/3 plus 1/4? The answer is, well, this is 4/12 plus 3/12. So 7/12 minus 1/12. So this is actually a probability of 1/2 and 1/2. And then here, the probability of picking a red is 0 because we don't pick out of anything. So what are these probabilities here? So the probability of picking out of both, so that's the probability of 2 coin flips coming up heads, right? So this is heads, heads, which is a probability of 1/4, right? It's 1/2 times 1/2. And then the probability of neither is also 1/4, because it's the probability of tails, tails. The probability of just heads on one of them, this is tails, heads. So this is also 1/4. And this is heads, tails. So this is also 1/4. So, oh, that's very nice. Look at that. Look how nice that is. So this tree has a bunch of branches. So what is the probability that at least one red ball is drawn? So we want to try to calculate this. So it's basically this. It's 1/4 times the probability of red, which is in this case 1/3, plus another 1/4 times the probability here, which is 1/4 again. So actually, we could rate this as the 2/8, if you like. Plus another 1/4 here, times the 1/2. Whoops, write it like this. And then the last one is plus a 1/4. And then, of course, here, the probability is 1 that you will get nothing. So you multiply that by 0. And so here, what do we get? Here we get 1/12. Here we get 1/16. Here we get 1/8. So it's 1/12 plus 1/16 plus 1/8. And of course, when you add all this together, this is what? I don't even know. It's I guess you'd have to convert them all to 48ths. So this would be like 3/48. This would be, this would be 4/48, 3/48, and 6/48. So I think overall it is 13. Am I right? 13/48. So yeah, 3 plus 4 plus 6, I guess. And yep, I think that's right. So this is a weird problem, right? Mainly because we had to kind of do this thing here. Now, I guess technically, if you wanted to, what you could have done to kind of simplify the process is, well, I think this is fine. I mean, I don't know. You could have done like a double tree here where you just had like the first coin flip as heads, tails, and then you could have done the second coin flip as heads, tails, and then of course then you branch into like you either pick red or not, pick red or not, pick red or not. So that would be a more classical looking tree, and it's essentially equivalent to this, but it's kind of more well thought out in hindsight. Okay, let's see. Oh, okay. All right, so this is a pretty standard type of question that you might be asked. So let's go through this at least once. This is, unfortunately, given the current circumstances, this is almost kind of relevant, but let's pretend it's not relevant, right? Let's just pretend it's, pretend. Okay. Yeah, I know. So a medical test is not completely accurate. So really what they should say is almost all medical tests are not completely accurate. So when people have a certain disease, are tested, 90% have a positive reaction. So we have to think about this. So this is the probability of a positive given that they have the disease is 90%. So it's important that you read this kind of stuff carefully because it says like when the people who have certain diseases are tested. So this means like when you see when, you can think given, right? If you see if you see assume, if you see, assume the person is, has the disease, then 90% have, blah, 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 blah. So okay, but 5% of the people without the disease also test positive. So what that means is the probability that they test positive, and you can write this as like either disease complement or like not disease or whatever you want to say, is 5%. Oh God. I just stole this problem, so. Okay. So in a certain place, 20% of people, so the probability of D is 20%. Let's do a more realistic number, and I mean, unless you're talking about New York City right now, this is generally way too high. Let's shrink this number to like 2%. Because it's usually even less than that, but that'll make it a nice kind of round number to play with. So a person from the city is chosen at random and tested. So if the reaction is positive, so here's an if. Yeah, it's realistic right now. It's not generally realistic, but it is now. I don't know if you guys heard about the antibody test, where I think it was like 21.2% of people in New York City tested positive for COVID-19 antibodies. But there's a lot of questions as to what that means. So, okay, so cool. So now, if the reaction is positive, so remember that's the given part. So now we're going to assume a positive reaction. Yeah, so this was just from like a copy paste error. What is the probability that the person has the disease? And immediately when you see this, right, your first thought should be Bayes' theorem. And the reason why is because what you know here is you have the world is partitioned into those people with the disease and those people without the disease. And here's the people with a positive test. And you want to know, given that they have the disease, so given they're in this block, what's the probability of a positive test? And so the answer is, we actually have to use Bayes' theorem to compute it because we have all these other numbers. So remember, Bayes' theorem is going to say that this is equal to the probability of plus given D. And that's the whole point here, right? It allows you to swap the order of these symbols times the probability of D. And then remember that when you do the denominator should have at least, so it's going to start with the probability of plus given D times the probability of D plus, and then the hint is that this is the other one. So the probability of plus given D complement times the probability of D complement. Now, if we're going to compute all this stuff, then the good news is that we have that this is 90% times 2%. And then here we have the same thing, 0.9 times 0.02. And then here's the part that's tricky. We know that this is equal to 5%, so this is 0.05. And then what is this number here? So the probability of D complement, right? Probability of D complement is 1 minus the probability of D. So that gets me a 0.98 here. So overall, what we end up with here is, I guess we actually have to calculate. So what is this? This is 0.018 divided by 0.018, and then 0.5 times 0.98. I don't know. I mean, I guess I could think about it, but I'm too lazy. So, okay, so that's that should have been obvious in hindsight, but it's okay. Yeah, 0.049. And so, yeah, you're almost right. You just lost a 0. But, okay, cool. So, all right. 0.18, I'm sorry, yeah. Divided by... So as it turns out, this whole calculation just gives us 26.8%. Like this. So what did we just answer? Let's go back and check. what we just answered is, what is the probability that someone has the disease given that they've come in with a positive test? So they come into the hospital, they get a test, and it comes up positive, right? So if the disease is low enough in the in the population, like 2%, right? If it's low enough, then actually the probability that you had a false positive was much higher. Yeah, it's important to understand what you've just like calculated. So what if this was 20%? So let's just do this with 20%. So how does it change, right? So it changes because then these two things flip, and this becomes 0.8 rather than 0.98. Yeah, so a test with a 90% reliability, but a 5% false positive rate is actually, if whatever thing you're testing for, even if it's not a disease, even if it's some other thing you're testing for in just a population, has a low enough kind of incidence rate, you're gonna see a lot of false positives if you do this kind of thing. So we'll talk about a way to improve this a little bit. Yeah, we should just do that. But then the other thing to say is, what if we just change, is this a common issue in statistics? It's a common issue in medicine, yeah. Well, as with all news, it's important to understand what it actually means. So, okay, so if we do 0.9 times 0.2 divided by, let's see, okay, 0.18 plus 0.05 times 0.8. So if the disease, on the other hand, if the disease is now at a 20% rate in the population, this number changes, actually. So it's 81% of people who test positive have it, if it's 20% in the population. So it really depends on... So I will say that this is actually a true difficulty, for instance, in coronavirus testing, because if we assume even lower numbers than this, then the actual answer is, if we tested everybody in the country today, most likely the number of false positives, yes, exactly, the number of false positives would probably be higher than the number of actual true positives. If of course the incidence rate of the virus is as they say. So that's kind of the problem with some of this stuff. Well, yeah, of course, if you could do that. So let me show you how to do that, or let me show you a way to fix this problem a little bit. So if people come up positive, let's say that we're doing it with the probability of disease is just 2%, right? So that we're in the low incidence case, and the probability of a positive test given the disease is 0.9, and the probability of a positive test given the disease complement is 0.05. So these are the same numbers from before, except now what we're going to do is we're going to just test all the people who come up positive. We're just going to test them twice. So here's the tree. So either you have the disease or you don't. If you have the disease, you can either have a positive test or a negative test. And then if they come up negative, so this is kind of the bad case where they have the disease. This is the quiet problem, that it's hard to, this is the hardest thing to detect, is you have the disease, but you come up negative on the first test. So there's no more indication that you're going to get, you're not going to get tested again, but you actually do have it. So if we just label this stuff, but then we test the people who come out positive, And so say this is 0.05, and say this is 0.95, which we're never actually going to use, but it doesn't matter. And then if they have the thing, then there's still a 0.05 chance that they're going to come out positive. Now we have to assume independence here of the two tests. Yeah, I mean, so we have to assume that there's not something weird about those people. Like some people will test positive because of exposure to a virus and they develop antibodies, but they've never actually really, it's kind of untrue to say that they've had the illness. They just were exposed and have antibodies. So, for instance, in those kinds of tests, you'll see things like that. Okay. So if we test again, right, this is the test again. Then, as it turns out, what we need is the probability, we want to compute the probability that you have the disease given you got a positive test. So that's still equal to, it's basically equal to this. The probability, given that you got 2 positive tests, right? That's what we really care about. So if you get 2 positive tests, then that's equal to 0.02 times 0.9 times 0.9 divided by 0.02, 0.9, 0.9, plus this path, so 0.98 times 0.05 times 0.05. So let's calculate this number. Okay. Let's add. And calculate. Okay. So this is way better. Because if you remember, the initial calculation only gave us, so yeah, what this number means is that if you have the disease, if you've tested positive twice, right? If you've tested positive twice, there's an 86% chance that you have the disease, right? That's what this number means. And so, yeah, so if you've tested positive twice, maybe I'll even type it in here. So, if you have tested positive twice, you have 86% chance of actually having it. So what we see is that if the test had a rate of false positives, which was this high, and was kind of, if the test had these parameters, then yeah. So if you did it 3 times, you'd be even more likely, and if you did it 4 times, you'd be. Now, of course, we're assuming that the tests are independent, right? So it's not always true, so we're assuming tests are independent, which is not 100% true, but of course that's the whole point of statistics, is that you have to kind of assume something or else you can't compute anything. So here we're assuming the tests are independent. If they were actually not independent, then probably the right answer is not to use the same test, but to use a different test, right? So if the tests aren't independent, then you use a different test for the second time. So, if they're not independent. So that's the general gist of that. So does everyone feel uplifted now? I think. Did I just copy the same thing twice? Was that the same exact? I think it is. So good. Let's see. Yeah, I mean the problem with the more times you test negative is that, like, most of the time, if you come out with a negative test, sure, we can do a little graph theory. You want to do graph theory? I want to do graph theory. You know, this literally was just copy pasting. So the book I got it from, what I'm going to say about the book I got it from is Great Problems. Bad copy editing. Okay. Yeah, so let's do a few minutes of graph theory, because that's fun. What is the name of the book that I don't even know. Let's see if I can find it. If I still have it open. I don't know what I did with it. I think I might have closed it or something. Yeah, I have a bunch of stuff open, but I don't see anything obvious. I'll have to find it. Okay. So, what is a graph? Oh, thanks. Well, the good news is it's very unlikely, because I think we're allowed to comment. You know, this is like educational stuff, and so DMCA can't get me for it. I don't think, right? So okay. So a graph is a pair. So what we usually say is it's a set of vertices and a set of edges. Oh no, I know that. So my friend is teaching a differential equations class, and he played some really obscure, like, techno music, and already had one of his differential equations lectures removed off of YouTube for that exact thing. So you don't have to play Katy Perry. Okay. Anyway, so a graph is a pair of sets, right? VE, where V is a collection of vertices and E is a set of edges. So a singular vertex is called a vertex. You can also call them nodes. Sometimes I'll call them nodes. In computer science, you'll hear them called nodes. So basically, let me draw some examples of graphs. Here's some examples. There we are. Maybe I'll draw them with thinner lines connecting so that it's more obvious, like this. So, well, I mean, graphs are like linked lists on steroids, right? So, yeah. Anyway. Okay, so other than filling in the dots, which is morally correct, so let's pay attention to well, let's not pay attention to the difference between a directed or an undirected graph yet. Let's talk about a few things that I'm kind of excluding that can happen, right? So this definition of graph is usually called, or at least in some books, it's called a simple graph. And the reason why it's called a simple graph is because it doesn't have this. It doesn't have multiple edges connecting the same two vertices. Like this type of thing is definitely possible in some version of graph theory. So when you define what kind of graphs you're working on, you have to explain to your reader what kind you're actually going to be talking about. So here, this is a graph that allows for multiple connecting edges, and it also will allow for, say, loops between edges like this. So you can have, or I should say, loops on the same vertex. So this one is kind of the most, and you can also have a completely disconnected part of the graph over here, right? So this could all be a graph, right? This is gamma 1. Yeah, loops in general in graphs are pretty bad. The reason is because if you're ever trying to find like the shortest path, or I shouldn't even say the shortest path, if you're trying to find, I guess actually, yeah, if you're trying to find the longest path, that's the real problem for it. The shortest path, when you have loops or multiple edges, obviously will just never take a loop, because if you took the loop, then the shorter path says don't take the loop and just go to your destination. So if you're going from here to here, you could go around here 20,000 times and then up and around, and that would be a path. But the shortest path is usually more well defined than the longest path. If you're actually looking for the longest path, if there's a single loop, right? If there's a loop in the graph, then the longest path is infinity, which is I guess it's a slight issue, right? All right, so let's draw some other graphs. So here's a graph. Here's a pretty simple one. There we are. That's a triangle. It has 3 vertices, right? So the set of vertices is going to be like v1, v2, v3. And the set of edges is going to be the set this. It's going to be v1, v2, v2, v3, and v3, v1. Sure. So the real question now is, if we look at a graph like this, do we want... So here's the 2 directions in graph theory that you can go. Most of the time, you're going to talk about undirected graphs. So there was a computer science project last semester about directed graphs. So let me just explain the difference. Directed graphs, so if this is a digraph or a directed graph, I hate the term digraph because anyway, it confuses me for some reason. I can't even explain what the true origin of the confusion is. So if I say that you can get from, say, v2 to v1 like this, say this is v3. Yeah, so this is, yeah, some of you remember Project 1 from last semester. So here's the thing. So now this is a digraph. So a digraph has directions on all the arrows, right? So the point is that in an undirected graph, if I can go from, so let's draw the 2 equivalent graphs, or the 2, like, shouldn't say equivalent, but the 2 kind of analogous graphs in the 2 languages of directed or undirected. So this is v1, v2, v3. So this is going to be the undirected. And so in an undirected graph, if I can go from v2 to v1, I can go back from v1 to v2, right? What this means is that each path is like a road. I can go back and I can go forward. I can go in either direction. It's fine. So if this is connected, I can do this. If this is connected, I can do this. So, but in this directed graph, for instance, there's an edge that goes from v3 to v2. So we can have a path that goes from v3 to v2, and then we can go from v2 to v1. So this is like a path here. Path would be v3 to v2, v1, but here's the problem, right? And this is not necessarily a problem as in directed graphs are bad. This is a problem as in this is something to be aware of if you're dealing with a directed graph. You can end up somewhere, and this v1 node is like a dead end, right? The reason why it's a dead end is because you can go from v3 to v1, but then you're stuck. Or you can go v3 to v2, and then you're stuck. I'm sorry, v3 to v2, v2 to v1, and then you're stuck. So you see that unlike here, where you can kind of go, oh, I'm going to go from v3 to v2 to v1, then back to v3, then v2, then v3 again, v1. I can traverse the graph in any direction. Here, I can only go in single directions. Now, you can always make a digraph, which is the same thing as a regular undirected graph. And the way to do it is you just add in all the other edges. So if two things are connected in one direction, you just connect them in the other direction too. So if this one's connected this way, you just add another edge that goes back along here. If this one's connected this way, then you can just go back. So basically here, you have to pretend like this is like 6 edges. But these are like 6 directed edges. And then these would be 3 undirected edges on the graph. Yeah, v3 is uphill. So if you go anywhere, then you've restricted your options. Okay, so that's basically what a graph is, and that's the difference between a directed graph and an undirected graph. Okay. Let's see what else I got for you. Here we are. So here's the famous bridges of Königsberg problem, or whatever. So this is the graph that that was drawn based on it, and the edges are numbered because I don't know why. So Euler wanted to know if you could, so each one of these is like a destination. So this is like a blob, this is a place, this is a place, this is a place. So you have 4 places, and you have 7 bridges, right? Yeah, it does look like a... Actually, I'm not sure what you would call a helmet of that kind. So I wanted to know if you could cross all 7 bridges without repetition. And so what he wanted ended up being called, because he kind of invented it. He invented the thing, and now it's called an Eulerian path, or Eulerian cycle. Maybe you could call it a cycle, or circuit. Yeah, the answer is actually no. And so if you don't believe us, right, then you can kind of try it out for yourself. So say you go from A to D, then you go here, and then you go here, and then you go here, right? And then you'll go here, and then here's your problem. You can either you can kind of head back this way, or you can do this. But if you do either one of those, then what do you see that just happened, right? And then you think, okay, well, maybe I started in the wrong spot. Maybe I did something wrong. So let's erase all this and try again. So let's say I start at B. So if I start at B, I'm going to start up here. And then since this is symmetric, it doesn't matter, so I'm going to head down to A. And then you only have one choice. Since these are symmetric, you have this choice. And now here you have a different choice. But if you go back on this path, you're going to intersect the same path, so you can't do that yet. So you have to go this way. And as I say, this is symmetric, so you have only really one. You have two choices, but they're the same choice, really. And then here you can go back like this, or alternatively, you can go up here. But if you go up here, you see that you can't go and use these paths again. If you go back here, then you see that this path is. So as it turns out, there's a theorem that'll tell you when you have an Eulerian path, and so it's a pretty cool theorem. So, wow, that's a pretty heavy and correct observation there. So the theorem basically says that if any, so let me just define something for you. I want to define the degree of a vertex. It's equal to the number of edges incident. Ugh, that's literally the worst thing ever. The number of edges that, maybe I'll just say that touch. The mathematical word for it is incident to, so that touch that vertex. So the degree of a vertex V is the number of edges that touch it. So here we have 1, 2, 3, so the degree of A is 3. The degree of B is actually 4. Oh, I'm sorry, the degree of B of 5. Degree of B of 5. The degree of C is 3 again, since, by Michal symmetry. And the degree of D is 3, again by symmetry. So all the degrees are odd, right? All the degrees are odd. Now, as it turns out, if a single degree is odd, it suffices to show that there's no Eulerian path. So, okay, so here's two definitions. The definition here is that the degree of a vertex in a graph is the number of edges incident to it, and so I've told you what incident means. So we can define the degree of a vertex as deg v, for v in the vertices of some graph. Okay, so this is what I've said before. And then here, gamma is a graph. Then an Euler circuit for gamma is a circuit. Basically, that means a path that comes back to the same point, right? It's a cycle or a circuit. Basically, that means that it starts and ends at the same point. Okay. And here's the theorem, which I guess we'll have to talk about maybe next time, but still, I'm going to introduce it now. If a graph gamma has an Euler circuit, right, then every vertex has positive even degree. So the positive bit is a little bit of lawyer nonsense that just says that you don't have any isolated things. So for instance here, like if this were a graph, each of these vertices here has degree 2. But this one has degree 0. And so that's why there's not an Eulerian circuit, because it doesn't touch every edge. Or basically that's kind of it doesn't go through every vertex. So, okay. So then each vertex of the graph has positive even degree. So actually the proof of it, this might be one of the only significant proofs that I do in graph theory. I'll probably cover it next time, I think. Maybe I'll do it next time. But it's actually pretty cool because I'm going to say that it's an intuitive proof. So an Eulerian path is a path that covers every edge. So that means that it's a path where you visit every edge exactly once, right? And so here, if you do this kind of thing, that's an Eulerian path on this graph. Yep. All right. Cool. So that's a little taste of graph theory. We'll do more graph theory next time, maybe, and then maybe talk a little bit about Big O. Yeah, I want to talk about, my goal in graph theory is to talk about Eulerian paths, Hamiltonian paths, and then maybe I want to talk about Ramsey theory just a little bit. And so yeah, the Konigsberg bridge problem, very right, because basically you can say here the contrapositive of this theorem says that the contrapositive of this theorem says that if the graph has even one vertex of odd degree, then it cannot have, right? Because not this implies not that. So if it has at least one vertex of odd degree, then it can't have an Eulerian circuit. So that's this theorem is like pretty amazing. I wish I could say, so the reason why Eulerian paths are nice is because they're kind of easier. Hamiltonian paths are worse in a sense, because there's not quite a theorem that's like this, right? It's not quite as strong. So it's just not, there's a bunch of theorems about it, but none of them give you the same kind of absolute power that this one does. So yeah, we'll talk a little bit about Ramsey theory, and then we'll maybe talk about bipartite graphs. And the marriage problem. And then maybe we'll talk about the four-color theorem. All right. Well, I'll leave you with this. Here's K8. Isn't that nice? Without knowing anything about it, it's still pretty cool, right? So will there be a homework release this week? I might try to write something up tonight. Maybe I'll make it kind of... Oh yeah, the other thing I wanted to talk about, planar graphs. Oh, it looks like Sim, doesn't it? Yeah, that's where Ramsey theory comes in, man. Oh. Maybe we can talk about the hero of all mathematicians, Paul Erdős. Okay, I'll let you guys go now. It's been fun. You know, when I tell you the story about Erdős, you'll understand why he's the hero. Okay. Have a good night, everyone. Time for me to go and chase a bird or make dinner or whatever it is I do. All right, guys. Yeah, I might send out like a homework either today or tomorrow. So stay tuned for that. Yeah, have a good weekend, everyone. thanks for watching some graph theory. Hope it was fun.